All right, so here is where we stopped. So simple grammars just had pairs of non-terminal to terminal pairs. So we have, if we're looking at a set, you can even think of it as a tuple, honestly, is every one of these a separate element. So the tuple here would be like S comma A, S comma B, S comma C, and we just can't have any duplication in this list of tuples. So because there's no duplication in this list of tuples, then we accept this as a simple grammar. This is not a simple grammar because you would have SA, SB, SA again, and then SC. And because we have two tuples that are the same, referring to this S to A and S to A, that are the two terminals, it's not simple for that reason. And we have that duplication if we were to list out these tuples. All right, we don't cover simple grammars too much or think about them too much for the rest of this class. But they are a subset of interesting idea, and I think they come up one more time as we talk about it. But the main thing from last time was dealing with grammar ambiguity. And we mentioned that if there's some string in the language that's defined by the grammar, can have multiple different parse trees constructed that derive it, then the grammar is ambiguous. This is a very bad thing. So as an example, we'll take the grammar that we said maps to mathematical parentheses and or curly braces. So we can now have successive scopes in addition to recursive scopes. So think about constructing AABB from this grammar. If there are multiple different parse trees, not just left to right or right to left parsing, but it's ambiguous if we can actually construct two different parse trees that look different. So how can we do this? We know we want to create AABB. So we could, as an example, go from S to, actually go straight down to SS, and then branch this. Each one of these S's becomes AS. I guess we need two A's in a row, right? Mm-hmm. AABB, so we're not, this would be ABAB. No, we can still do it. So this becomes ASB, this becomes lambda, this S becomes ASB. So we carry this A, this becomes A, it's a single line, ASB, and then this becomes lambda. So now a depth first search through this returns, I probably should have done this as three separate. Let's do that, there we go. So depth first search through this returns A, B, B. And we get AABB. On the other hand, we could go from S to SS, and now we're going to turn this first S into a lambda. This second S is going to go into SS, and this last S is going to go to lambda. This S is going to go to ASB, and this S is going to go to, actually, let's have some more fun. This S will go to SS, and this S will go to lambda, and this S will go to ASB, and this S, well, why not? We'll end the fun and go to lambda. You can see how you can create an arbitrarily complicated tree with SS's where one of the S's goes to lambda, and just you hunt for whichever other S and expand that one in the same way. So very different parse trees, but they generate with a depth first search the same string. If we depth first search this, we see that, really should have two of these, but we depth first search through this and find that we get A, B, B. And it's exactly the same result as we go through that depth first search. So two different parse trees generating the same string. With a single example of this, we can show that a grammar is ambiguous. Does the concept of ambiguity make sense? Questions about that? You can see how there are actually an infinite number of ways to make AABB with this. So not only is it ambiguous, it's disgustingly ambiguous. Or even simple strings. So why would this be a problem? Anyone need anything else for the board?
I can see it being annoying in like the case of like a compiler when you're or like just trying to follow every single possible combination can be a lot of work.
Well, imagine that I write a program and the compiler thinks that I can read it in this way in this order or this way in this order. Is that going to create some issues with regards to the associated underlying logic? Potentially. When you write a program, there can only be one way to read that program. It can only have one possible meaning. As soon as the compiler gets to choose what your program means, then what happens from a software engineering perspective? That's right, you kill people. Oh, you didn't mean to dose them with a reasonable dose and instead dose them with a lethal dose? Oh, my bad, it was ambiguous. That's an extreme example, but the point is valid. So unfortunately, we see ambiguity frequently in natural language. This is why English is a terrible language, and you should not learn it. And instead, everyone should just speak in programming languages, or logic, or math, or proofs, or Latin. No, Latin still has a little bit of ambiguity, but it's better than English.
I mean, English has a word that's its own opposite. Like, come on.
Yeah. So in programming languages, we cannot have ambiguity at all. There can be none of it. Unlike in natural language, where some ambiguity doesn't usually lead to the end of the world. In programming languages, ambiguity is a death sentence. So we need to remove it in every sense that we can. So frequently, not always, but very frequently, an ambiguous grammar can be rewritten to remove that ambiguity. And that just means that if you had come up with a grammar that is ambiguous and there is an existing grammar that you could make that is not ambiguous, the unambiguous grammar is going to be better. So here was a couple of examples of generating AABB. So as we've seen, grammars can start to be used to express some parentheses and of the sort. Imagine, on the other hand, that we could map entire mathematical expressions. Here is a grammar that looks like it's going to represent mathematical expressions. It allows for parentheses, multiplication, and addition. Hot diggity. So, my question for you is this grammar ambiguous? If so, how or why? Or if not, why not? Yeah.
I don't think it's ambiguous because if you want to have like a certain path, you have to follow that. Like if you want A plus B, you have to take E, go to the addition set, and then each of those E's have to go to I, and then those I's have to go to their respective values. And I can't see a way in which you'll ever be able to double back and then create something. The only, I guess the caveat is you can throw parentheses in wherever, but like that doesn't change the expression.
I give you this. How do you solve it? Is there any way that this grammar tells you how to solve this? Order of operations is not built into this grammar at all. So it either relies on an outside knowledge of the order of operations, or that the user is putting parentheses around the associated order of operations. And that's not good. If you're going to rely on your user to do something that you could handle yourself, if you have any experience with software engineering, that's usually a bad thing. You want to make it impossible for the user to hurt themselves, or at least verify that that's what they want to do. From a compiler's perspective, all of this should be done underneath the hood without the user having to think about order of operations as they type it in. Have you ever thought about order of operations when you write mathematical expressions in a programming language? I mean, you have to solve, make sure that you're doing it correctly, but assuming that you were to write something plus something times something, does the compiler do that correctly? It does. So there must be something built into the grammar that allows it to recognize that innate order of operations, which this grammar does not do. So, yeah, just having A, B, and C variables for simplicity. There is no order of operations. Whatever comes first is what's done first if we're parsing this left to right. Whatever comes last is parsed first if we're reading right to left, but that's not defined either. So this is an example of ambiguity in its greatest form. You would not be able to evaluate mathematical expressions if this were the underlying grammar, or you, the programmer, would be responsible for defining your own order of operations every time. So we could evaluate A plus B times C as such. And if we do it like this, what is the result? What is the order of operations of this parse tree? Are we doing the addition first, or are we doing the multiplication first?
The addition.
Are we?
Can you do it depth first?
We are doing depth first, but in order to know what this value is, to be able to add it to the first value, we have to have evaluated the entirety of the multiplication. So it's kind of a left-right node type of recursive depth first search, where we can't evaluate this addition until we evaluate this multiplication. So you can think of it as kind of a bottom-up parsing, where we take the E, which is A, so we're going to say A plus something. We can't evaluate this until we have something to plug in here. So to figure this out, we're going to create a new expression recursively that is B times C, which we can now evaluate and plug into that. So recursive thinking. So the multiplication happens before the addition. Even though the addition happens at a higher level of recursion, we see the addition first. We can't evaluate the addition until we evaluate the multiplication, because it gives us an important piece of that addition. On the other hand, we can do it this way. What is this doing first? This one's doing the addition first. And we find that we can do A plus B, and we get that entire evaluation at the lower levels of the tree before we multiply it by C. So two different parse trees, two different orders of operations. We do the addition first, or we do the multiplication first. And we get a very different mathematical response given that. You can imagine if you wrote in a programming language some mathematical expression, and sometimes when you ran the program, it gave you one answer, and sometimes when it ran the program, it gave you another answer. That wouldn't be good. Math needs a right answer. It needs to work according to the laws of mathematics. It can't just ignore the order of operations or change the order of operations. So how could we do this? How could we remove the grammar, remove the ambiguity from that grammar? So we can use precedence in the same way that we do in mathematical operations. We can do exactly the same thing in a grammar that forces us to evaluate certain aspects of the grammar before other aspects of the grammar. So we can rewrite the grammar to encapsulate outside precedence rules. Question?
No, I have a comment.
Yeah. Yeah,
In order to make the grammar get its order of operations right, you just gotta sit it down every once in a while and explain PEMDAS to it.
and then it forgets it the next day because it was in one ear out the other. You didn't tell me why. You didn't give me an exam with it. You gave me an exam with it, I just crammed for it, forgot it the next day.
I feel like this is exemplary of something that you've experienced at this point.
It's not a meta commentary, trust. So how would you handle trying to do this? Anyone want to take a stab? Maybe it's worth taking the last few minutes of class. See if you can think about and rewrite this grammar in a way that removes the ambiguity from it. This is not an easy or trivial change.
The only way that I can think of is like, you just throw in parentheses like everywhere.
We don't quite have to do that. That's a good, that's an idea. That's certainly an idea.
It'd put the fun in function, or put the fun in dysfunctional, but like, yeah.
So we want to evaluate parentheses before we evaluate multiplication, before we evaluate addition. How could we force that order in this grammar? What changes would we need to make to it in order to force that evaluation order? And the hint that I will give you is you need more non-terminals. These can't all just be E's. Spend a few minutes, the last couple minutes of class, and think about it, and we will come back to it. You get an answer. So this will be my challenge for you for the day. I'll have office hours starting after my next class, so feel free to swing by with homework questions. Any other questions, concerns about the exam? Remember that I do need your exams back before you leave. Please don't leave without them. I have not entered them in Canvas, and that is the way that I ensure that I get them back. If I don't get it back, I don't know what score you got.
Please don't leave with them.
Sorry?
So did you mean to say, please don't leave with them?
Yeah, did I say please don't leave without them?
Yes. Speaking of ambiguity.
Yeah, right? Natural language. That was just wrong. There wasn't ambiguity. I just said the wrong thing. That's a logic error, not a runtime error. Yeah, please don't leave with them. I need them so that I can get you credit for it. But yeah, we will come back to this tomorrow. May this haunt your dreams.